Alrighty, good morning, everybody, and welcome to the wolfSSL live webinar on Secure Element or TPM, protecting your IoT product with Senior Engineer David Garske. My name is Kajal Subkota, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you would like to ask the question live, as we do host a Q&A session following the presentation. This webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I also invite everyone to follow us on Twitter at wolfSSL, as well as all of our other socials. And please feel free to email us at facts@wolfSSL.com if you have any additional questions. And now I'd like to give a brief company overview before we move on to the technical presentation. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source dual licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 40 dedicated employees in 2021, most of which are engineers. This progress is, of course, supported by a strong partner network that we're very proud of, which includes DDCI, STMicro, and RTI, for example. Since the beginning, our engineering team have developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and a FIPS-ready offering, MQTT up to the version 5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfBoot, as well as Java wrappers and JSSC support and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'm going to hand it over to David for the presentation.
Thanks, Kajo. Hey everyone, my name is David Garske. I'm a senior engineer at wolfSSL, and I'm based in California, in case you're wondering. And today we're going to talk about how to protect your IoT products using external secure elements. This slide also talks about our licensing and that we're open source. So a couple things with IoT security is the security areas that you should focus on. So one would be firmware updates, making sure that your updated partition is, making sure your update is actually signed and valid and it has an anchor that's in a root of trust. Any private keys that are used, these are asymmetric keys, like a key pair, public private key pairs like RSA or ECC, those need to be protected. Any encryption keys that are used, symmetric ones like for AES or Cha-Cha, those should also be protected. And then any IoT products that have external interfaces like an I2C bus, or let's say your JTAG, those should be locked. And then if you have sensitive data, it should be encrypted at rest. I'm not going to talk a lot about software-based solutions, but I am going to mention that they are very difficult and complex to get right. It's really difficult to provide real protection for the private keys. I talk about that a little more. And they require leveraging something like a trusted execution environment like ARM's Trust Zone or Intel SGX. And if you just had a curiosity, I looked up the number of vulnerabilities around these, and there are a significant number, which actually surprised me. So some of the trends we're seeing in IoT security are that security is starting to be considered earlier in the design. And I think a lot of that's driven by, mandates coming down. Another one is the increased demand for a secure element, like a dedicated chip specifically designed for protecting keys and offering security. Another one is seeking standardization of the devices and interfaces. And so a lot of what I'm going to talk about today is a comparison between secure elements or crypto coprocessors that are out there and TPMs. Those just happen to be areas that I'm very familiar with. And we're seeing a demand across many industries like automotive, aerospace, medical, industrial, and smart homes, and lots of other edge devices, pretty much anything you can name. And the protection of the asymmetric private key is really, really critical. The other thing we're noticing as a trend is that TPMs are being used in embedded projects as well, not just PCs. So some of the mechanisms that these vendors deploy to ensure that the system is secure is they'll do things like differential power analysis, side channel attack resistance mechanisms. So they'll make it look the same, like they'll use timing resistant code, and they'll make it so that an operation can't be reverse engineered or inspected by some kind of physical analysis of the chip. They also, most of them have tamper resistance. So if somebody tries to, decap the chip and read it, there's mechanisms in there to prevent that. Well, prevent reading. I don't know if that's fully true, but some of them do. And then there are mechanisms for brute force attacks. So if somebody's trying to brute force, a password or something to get to the chip, usually they have lockouts for those. And then more importantly is the secure storage for keys and data. So secure non-volatile storage specifically designed for storing keys. And then they'll employ encryption of the communication interface. And another really important one is a source for true random number generation in hardware, which produces good secure keys. All right, so we're going to talk about the difference between TPMs and what I'm calling secure elements. So the TPM has been driven by the Trusted Computing Group, which is made up of a bunch of large companies like Intel, Microsoft, IBM. And they have standardized the physical chip interface, the software API interfaces, the communication, over SPI, what that looks like. They've even, they have requirements for which algorithms are supported and at which level. So right now with most of the TPMs, the 2.0 chips that are out there, they support RSA 2048-bit and ECC 256-bit. Some support some higher levels in the current one. There is a new 1.59 PC, it's called the PC client specification, and they're bumping that up to the 3072-bit RSA and the 384-bit ECC based on NIST recommendations. So they've raised the bar for the minimum algorithm. Another thing TPMs do is they'll support measured boot using the platform configuration registers. So a great thing about TPMs is that you can, let's say you could hash the bootloader image, and you could put that hash into a PCR register. And later on down the boot chain or into your application, you'd be able to read that hash and confirm that it actually booted using code you expected. So most of the TPMs do have larger NV space. It kind of varies, and I'll go into a little more detail. They all support encrypted sessions. So they use AES CFB or XOR to start an authenticated session where you can encrypt sensitive data over the bus. SPI interface is pretty standard. There's also an LPC option, and then some vendors have an I2C support, and there's actually a PC client. There's actually a spec out there that TCG has put out recently for the I2C as well. And most vendors provide a mechanism to do firmware updates. Now, those are usually very specific to the vendor, but so far I've seen that most vendors have a way to do that. The other thing that's really important is the provisioning of the chips. So they've standardized this based on an endorsement key, and there's an EK certificate that goes along with that, that basically proves authenticity of the chip. And then there's some really advanced policy management. They're very complex. There's a lot in them. And I know the cost is higher than some of the secure elements. So off the bat, Secure Element, they're usually smaller and lower costs. There is no standard API interface between them. Typically, they only support ECC, although there are some newer ones emerging that support additional algorithms. The ones I've seen are all I2C interface. I have not found one that's firmware upgradable, at least made available, through any sort of NDA. The provisioning varies by the vendor, but I have found a couple of things. One is that each of the vendors has a really great system in place for doing provisioning and setup of the keys and certificates during manufacturing. It's also much easier to obtain low volume samples for development, including getting development boards. It's a lot easier. And I'm going to dive into each of these chips that we support in more detail here. The storage is definitely limited compared to a TPM on these as well. I did a quick table. It just kind of differentiates the hardware interface, the physical chip, and the software APIs, algorithms. Anyone who wants this slide, feel free to screen capture it or request the slides afterwards. It talks about everything we just talked about. Okay, so I'm going to talk more about the hardware we support. So right now, these are the ones that we support that do asymmetric algorithms externally. A new one that has emerged is the GSMA, the IoT Safe protocol based on SIM, and I'll talk about it a little more too. Additionally, the Microchip ATECC 508 or 608. The 608 is the newer model. And then NXP has this EdgeLock, this SE050 chip that they've come out with. It also has more than ECC support. And then we have the ST Safe A100, A110 support. And I'm going to talk about each of these a little bit more. So these are the TPM vendors that we have tested with and have support for the chips currently out of the box. This is a full list. I mean, there may be one other vendor out there that's not on this list, but this is pretty comprehensive. And then we have other on-chip accelerators that we support. I'm not going to talk a lot about these, but in wolfCrypt, we do have support for these. And if you are interested in any of those, just email us at, facts@wolfSSL.com. That's FACTS. So let's do a little bit of hardware comparison. So the IoT Safe, it supports ECC-based keys, and it actually does it in a SIM. So the protocol defines having crypto support in the SIM card. And this is something that GSMA introduced recently, and to my surprise, honestly. But so I've been able to do some of that development with another engineer, and it supports offload of ECC and potentially, I think, RSA and Diffie-Hellman as well. And that support's integrated into our wolfCrypt library. And there's an RNG source as well. And it actually is a protocol that goes over what I would consider a UART to communicate with the SIM. So another one is the Microchip ATECC. So it has an I2C interface, and there's a pairing that happens to encrypt the bus where you retain on the host side a key. It supports only the 256-bit prime NIST curve. It has up to 16 key slots that can be used for different purposes. And then there's about 9 KB of zone storage you can use for certificates. And Microchip provides many options for provisioning, such as their Trust and Go, their Trust Flex, Trust Custom. These are not field upgradable, and these are links where you can find out more about those and how to build with those. So the NXP EdgeLock SE050 is a new one we added. It also has an I2C bus with bus encryption, and it supports most of the asymmetric algorithms, so ECC, Diffie-Hellman, RSA, and ED and Curve 25519. It has 50 KB of secure data storage. This is in a pull request right now. It has not been merged into master. It's not in a release yet, but it will be soon. And they have a middleware that they call their EdgeLock middleware that you can build. Another one is the ST Safe, the A100 or the A110. Again, it's I2C. This one supports both the ECC 256-bit prime NIST curve and the 384-bit. There's 2 key slots. So one is a long-term signing key, and the second is a ephemeral key that can be generated for sessions. And then you can perform ECDH, shared secret against it. It has about 6K of storage for certificates in the NV. It's not field upgradable. And here's a link to where you can find more information about it. So they have a device library, and then we've also built up a middleware layer that helps with the porting that you can request from us. Okay, so this is an old slide that I pulled in, and it's a comparison of 3 of the modules that I was able to get information for. I was not able to get this for the New Baton or the Nations Tech. They're all pretty comparable, and there's there's nothing super significant here. They all have minimum algorithm requirements, and they've all got FIPS, certifications. I think some of the newer chips may have more NV space coming as well. This benchmark slide is also an old one I pulled in. I do have data for all of the vendors, and I realized when I was preparing for this that ops per second is kind of not ideal. I would prefer to say just that milliseconds per operation, but basically you can take this number. So 1,000 divided by 62 gives you the number of, how long it takes in milliseconds. Okay, well, if anyone wants that, it's available several places. And then this is the benchmarks for the SC-safe and the at ECC that I pulled in. I converted it to milliseconds here so you can get an idea. I do not have the A110 benchmarks for the SC-safe. Couldn't find those yet. Okay, so I wanted to talk really quick about wolfTPM. So what we have is an open source library that we designed for bare metal use. And it's designed to work with any of those TPM chips. It implements its own TIS layer, which is that transport interface for the SPI interface. We have lots of different examples and wrappers to simplify using those APIs. And there's no external dependencies. And of course, it supports parameter encryption, which I highly recommend using for the authenticated sessions. So here's a list of some of the examples that we have and wrappers to help. The TPM also, I didn't mention it, has a clock that counts the uptime in time since last reset. It's also got some great things like one-way counters. And in the newer TPMs that are coming, they have this X509 feature. X509 certified, but it's still coming down the road. And SPI is the most common interface. A couple of vendors have the I2C support. We support, using the SPI bus directly, but if you're on, let's say, like a Raspberry Pi, you could use the Linux kernel driver, devTPM 0. We also support using a wolfTPM inside Windows with their TBS, which is basically their TPM interface in Windows. And then we support using the TPM simulator. So there's several of them out there, but there's one from IBM we use that there's a script that shows how to build it and use it. And basically it stands up a server that has a couple of ports that you can connect to, and it behaves just like a real TPM, which is great for testing. So if you're using that native SPI interface, we have some examples. Here's a list of some HAL examples that we have, and we're adding to these all the time. So in the first half of 2021, here's some things that we accomplished in wolfTPM. We added remote attestation support with a make and activate credential. We added an example for sealing a secret with a key. And we added some examples for key generation of some metric keys, like let's say AES keys. And then we added some more examples for doing non-volatile storage and some GPIO support, which is a feature on a couple of the TPMs where they have a couple of spare IOs that you can use for either input or output. And yeah, I added endorsement hierarchy support, some examples and refactors some things. So this is a great slide. So we're the only stack that supports bare metal and the only stack for embedded IoT use and the only one that does GPIO. Great. So our second half, we're planning to do some U-boot integration, also an example that integrates with wolfSSH to show using public key-based authentication for SSH. And then on the parameter encryption, we want to add the ECC salt and the bounded session support. Those are definitely not required to do parameter encryption, but they're just extra features that we can add that didn't get implemented. Also, with wolfBoot, I didn't talk about it too much, but we offer full integration of wolfBoot with wolfTPM to be able to provide a secure boot solution. Potentially, you could have a root of trust based in a secure element or a TPM. And with a TPM, you could also do majored boot. So a wolfBoot is basically a bare metal implementation that has a partitioning scheme that allows you to do updates and version checking and rollback if there's a failure. We also recently added support for differential updates. So you can just send over the delta between two updates and then it will be able to update that and also roll back, which is pretty neat. And then we also have support for encrypted updates. So you can actually encrypt the partition as it's coming over the air. And then it's stored unencrypted once it's on the internal flash. It has the ability to be stored encrypted on external flash if you want. Let's see. Okay, so really quick, because I guess I've gone a little long here. So one of the things that I found is that the Raspberry Pi is probably the best platform for doing development evaluation of these. Most vendors have some kind of Raspberry Pi or Arduino board available, and it makes it really easy to interface with. And with our wolfTPM library, you can use any of those TPM 2.0 modules. Yeah, and I said all that. Okay. And this is a little deep dive. So we have a couple of features that allow callbacks at either the TLS layer or the crypto layer. And if someone is coming at this new, this is probably the best place to get pointed at. Most of those examples you saw have crypto callback and TLS PK callback references in those links. And if you're adding, let's say you wanted to add support for one we don't have, this is a great place to go, and basically allows you to register callbacks anytime there's going to be, like, let's say an ECC operation or RSA operation. So in summary, it is my opinion that hardware-based security is critical for IoT product security. Protection of the asymmetric private key is really critical. It needs to be generated in a secure area, and it should not be able to be read or exported. Another thing that's often overlooked is generation of the keys. It's really, really important that the generation, that the random entropy used for the generation of those keys is good. Because if you look, most of the vulnerabilities around some of the things that have come up is because there wasn't a good random seed used, or that the source for that wasn't very good. Another thing to consider is that these chip vendors have spent years and millions of dollars developing these solutions with security at the core design, not just in their software, but in the hardware design, which is more than we can do in just a generic microcontroller. Okay, so I've rambled on for a while, and now I'd like to take an opportunity to answer any questions. Let's see. I see a list here. Kajal, have you been reviewing it? Is there one in particular?
Yeah, we'll do it first come, first serve for these questions. So do you have any learning document or tutorial to do hands-on on wolfBoot? And which board would you choose to do hands-on?
That's a great question. Yeah, we do have lots of material, which I'm happy to share. In fact, I know we've done a couple of recorded webinars that are on YouTube. There is a document that I just found. It was a great blog series we did that went into really good detail about how to get started. I would actually say that the ST development boards are pretty great. We support most of those boards. I'm a little biased here just because that's what I've been working with. And if you go to there's a couple of videos that I've done as well that are on YouTube, but something like an STM32, F4, L4, or something like it. Doesn't matter, H7, F7. One of those Nucleo boards. We support most of those with wolfBoot out of the box. And then there's, like I said, materials that show how to do that.
Awesome. What is the difference between chip card-based systems, OS on a smart card, which means that there is a serial interface, hardware security module, and TPM?
Yeah.
How do we find these, I guess, similarities inside wolfSSL or wolfTPM?
Yeah, that's a complex question. When you look back at the history of these types of HSMs and smart cards, it really comes back to credit card chips, you know, the smart cards that are inside a lot of these chips, and the evolution of that eventually became the TPM. But the similarities between all of these are the one core thing I see is that they're physically capable of generating an asymmetric private key and protecting it. And then taking that key and then be able to sign something against it. And to me, that is the root of what we're trying to achieve here, by protecting the private key and providing a way to use that private key. If that is the minimum that's achieved with an HSM, that is great. So like, even if you took your TLS session and you generated your ephemeral key and did your shared secret in software, you only risk potentially exposing that one session. But if somebody gets a hold of that long-term private key, then they can impersonate you. The authentication of that is gone. You know, it's a big problem, right? So, oh, somebody noted that NXP part, the SE051, not the 050, is field upgradable. Great.
Yeah. And then how someone wants to know about NXP A71CH.
So I think we have support for that, and I've seen it come up, but I haven't worked on it. So we'll have to get back to you on that. Feel free to email us.
And someone also wants to know if we have support for NRF 52840. Yeah.
The answer is yes. So that's a Nordic part, and it has the ARM cryptocell. And yes, we fully support that. It's like the CC 310 or something like that. I mentioned it. I didn't include slides on it, although I had some stuff written up. So that is an on-chip crypto coprocessor. The main goal for that is basically to accelerate cryptographic operations. I did not find a way in there to securely create a key within the cryptocell. Now, if on that chip you also have trust zone, then it is possible to take that secure side and generate a key in the secure side and then make, you know, expose ways to use that. Like I said, it is a complicated thing to do. There are ways to do it. So.
Okay, awesome. And isn't rollback a vulnerability if you can roll back to a previously vulnerable version, thereby defeating a subsequent mitigation?
Absolutely. And let me clarify. So in wolfBoot specifically, we have rollback prevention. So there is not a way somebody could install an older version. Now, what we have done is we've provided the ability to fail back. So let's say you do an update and that update does not boot successfully. And let's say it watchdog resets before you can set the success. Anyway, what will happen is it will roll back to the last known working version that's still stored. That's the only thing. Now, the wolfBoot version protection, that's something that most people want. It's considered a feature, but it is something you could turn off at build time if you wanted somebody to be able to install an old version. Don't recommend it though.
Okay, fantastic. Let's see. Is it possible to remotely store a private signing key via TCP IP connection on a Raspberry Pi with TPM, and then afterwards to use the Pi device offline to sign the files?
Yes. It would. I think what you're saying is taking the actual private key, sending it over a network connection, assuming something secure like TLS, and then storing it on the Pi into the TPM. Yes. So you do have the ability to import an external private key to the TPM. That is possible. It doesn't provide all the same built-in protections, but yes, you can load an external private key and you can use that. And you can associate it with a password or authenticated session to help protect it. Okay.
Okay, awesome. What is your attacker model for secure boot using a TPM secure element? Basically, do you have to protect a public key from modification?
Yeah, that's a great question. And that's something I've mulled around in my head for a while. So we don't have anybody who's put the root of trust for the public key based updates into the TPM yet for that reason. And this question is suggesting that somebody could literally replace the TPM. Now, there are ways to detect compromise of a TPM, changing of a TPM, compromise of a TPM, changing of a TPM. And a lot of it has to do with those authenticated sessions, parameter encryption. So there are ways to do it, meaning you can put something like a public key in a TPM, and you can put it there in a way that isn't tamperable. And if somebody, let's say, swapped out the TPM for something else, you would be able to tell the difference, and you would be able to not boot, let's say. That's a great question. Great question.
Yeah. The next question is from Anish Agarwal. You have your hand raised as well. Would you like to ask your question live? I've allowed you to talk.
So I'll read his question. So he's saying that the NXP SE050 uses the global platform system to program applications on the device. Java Smart Card. How do you program a global platform app on something like the NXP, and does wolfBoot support this? That question's a little specific, and I don't have an answer for you, but feel free to email us directly, and we can dig in. So, we're a team of engineers. Lots of us have areas of expertise. That's not one I'm super familiar with. So.
Okay, awesome. Any tips on getting started with GSMA IoT safe support?
Yes. So the dev board we used is one from ST. And if you go to the link in the presentation, there is, let me see, it's right here. It talks about what we used to test on this evaluation platform. And you can get some good deals. And it actually used formatting's a little off here, but it used a QTEL, the BG96 modem. And we had to put some newer firmware on there, but we were able to run, I guess they call it these applets, but we were able to do the offloading to the SIM card, and we were able to have the keys based on the SIM and certificates too.
Okay, fantastic. Is wolfTPM ARM PSA API conformed?
No, so the ARM PSA is the platform security architecture, and it's an API definition for crypto interfaces. So wolfTPM specifically uses the TCG APIs, which are structured like TPM2 _. We've also made it so you can use wolfcrypt APIs, and you can offload to a TPM like a crypto coprocessor, but we do not have the PSA API implementation for that yet. There's no plan to do it for wolfTPM. Eventually, there may be an interface like that for wolfcrypt, though.
Okay, this person wants to know how to use PIC32MX with TPS 1.2 minimum PPP.
Yeah, so that's a Microchip PIC32MX, which is an older one. MZ is more common, and he's suggesting TLS 1.2 as a minimum. PPP, I think, is point-to-point protocol. I mean, that's super specific. So in wolfTPM, you can find in there examples for using TLS, and you can offload all of the asymmetric operations to a TPM. And some TPM support symmetric operations as well. So we have examples for offloading all of that to a TPM and demonstrate how to, for example, create a key, generate a certificate signing request, have a CA sign that, load that to the TPM, and use that certificate and key based on the TPM for a TLS session. So you go to wolfTPM on GitHub, and then go into examples directory in TLS, and you can find those.
Fantastic. And do you have a demo of wolfTPM on a Raspberry Pi device?
I think we've posted a few videos. I don't have my Pi on. I think if you go on YouTube and look up wolfTPM, you can find a few. And I'm not prepared to do a live demo of it right now, but with the simulator, you can run on any type of platform. It could be Windows or Linux or Mac, which is kind of fun to do development against or test against.
Okay, awesome. So Rodney McCraig has his hand raised to ask a question. I'm going to allow you to ask your question live, Rodney.
It says his mic's muted. Maybe he wasn't ready. I don't see his question. Maybe go on to the next one. I saw something like the TPM2 tools one.
Is there a need for any other tools like TPM2 tools or PKCS11 interfaces if one would use only wolfSSL solutions for provisioning TPM, MQTT, etc.?
Yeah, it's a great question. So the answer is no, you won't need anything like TPM2 tools or PKCS11. So let me clarify those things. So the TPM2 tools is a set of examples that are available in Linux. They're command line tools for accessing a TPM. We have similar type examples, and we've done some things to simplify those. So you can use those directly. PKCS11 is a standard for using an HSM. And usually those are more commercial grade external devices. PKCS11 usually uses a shared DLL to interface with. We do support that, but you wouldn't need any of those things if you were using just wolfSSL for TPM or MQTT.
Okay, fantastic. Regarding the SEO 50 in Java question in a JCOP card or in principle any Java card, as long as you have the necessary keys and rights, it's possible to download additional applets and afterwards use them. However, you need a different version. I guess it's just a comment.
It's just a comment.
Yes.
I could read that again if someone's interested, but it's it sounds like there is ability to use Java and JCOP Java card against the SE050. Not sure. So, all right, I think that wraps it up.
Yeah, I think those are the last of our questions. Thank you, David.
Oh, you're welcome.
For a fantastic presentation. As a reminder to everyone, this webinar is recorded and will be made available on our YouTube channel shortly after the presentation. Everyone will also get a follow-up email with a link to the YouTube video. And then if you'd like to receive a copy of the slide deck, please feel free to email us at facts@wolfSSL.com, and we'd be happy to send that over to you. And if you have any additional questions or comments, please also feel free to email us at facts@wolfSSL.com, and we'd be happy to answer. Before we go, there's one more question right here. I guess they're using an NXP IMX. Yeah, machine. And do you support the HSM on this chip?
Yes, so it has a CAM interface. It's very RTOS specific. So we have Integrity OS and QNX support for the CAM. If you're interested in further support, yeah, just email us and maybe provide some additional details about what you're doing. So.
Okay, awesome. And then I guess
Those look like comments, yeah.
Yeah, awesome. Thank you, everybody. I hope you have a fantastic rest of your day.